Hello students, today I am going to discuss the next important topic from the chapter States of Matter, that is behavior of real gases, deviation of real gases from ideal behavior. Already we have learned a gas which obeys all the gas laws or ideal gas equation under all conditions of temperature and pressure is called ideal gas. That means what? Real gases deviate from ideal behavior. We know all the existing gases are said to be real. The real gases deviate from ideal behavior. Hence, these gases are known as non-ideal gases. Okay? Okay. To test behavior of real gases, we can plot PV versus a pressure graph at a constant temperature. Okay. To test behavior of real gases, we can plot PV versus pressure graph. The PV versus pressure graph is the graphical representation of Boyle's law. Okay. Then here we know the PV versus pressure graph for an ideal gas is a straight line parallel to pressure axis. That means if the gas is said to be ideal, it must obey Boyle's law. That means the value of PV is constant. Then the graph is a straight line parallel to the pressure axis. Okay, then from the graph we can say that when pressure increases, the deviation of real gases from the ideal behavior also increases. So pressure increase ചെയ്യുന്നതോറും റിയൽ ഗ്യാസിൻ്റെ ഹൈഡ്രജൻ, ഓക്സിജൻ, കാർബൺ മോണോക്സൈഡ്, മീഥേൻ ഒക്കെ എന്താണ്? റിയൽ ഗ്യാസ് ആണ്. ഈ റിയൽ ഗ്യാസിൻ്റെ ഈ ഐഡിയൽ ബിഹേവിയറിൽ നിന്നുള്ള എന്താണ് ഡീവിയേഷൻ ഇൻക്രീസ് ചെയ്യുന്നു എന്ന് നമുക്ക് പറയാൻ വേണ്ടി പറ്റും. ഓക്കെ, ഓർ വി ക്യാൻ സേ when pressure decreases means when pressure approaches zero at very low pressure, the PV value of all the gases becomes equal to that of ideal gases. That means real gases show ideal behavior at low pressure and high temperature. Very important point. All the real gases show ideal behavior at low pressure and high temperature. That means as the pressure increases and temperature decreases, the deviation of the gases from ideal behavior increases. അപ്പോൾ pressure increase ചെയ്യുമ്പോൾ നമുക്കറിയാം gas molecules come closer. അതുപോലെ temperature decrease ചെയ്യുമ്പോഴും gas molecules come closer. Then some force of attraction must be operate between the gas molecule. അപ്പോൾ ഗ്യാസ് മോളിക്യൂൾ തമ്മിലുള്ള അട്രാക്റ്റീവ് ഫോഴ്സ് എത്ര കണ്ട് ഇൻക്രീസ് ചെയ്യുന്നുവോ അത്ര കണ്ട് ഐഡിയൽ ബിഹേവിയറിൽ നിന്നുള്ള ഡീവിയേഷൻ ഇൻക്രീസ് ചെയ്യുന്നു എന്ന് നമുക്ക് പറയാം. ഓക്കെ, യെസ്. Then here hydrogen and helium. For hydrogen and helium, as the pressure increases, the PV value also increases. Okay, and we can say these two gases, hydrogen and helium, show positive deviation. But in the case of the gases like CH4, methane and carbon monoxide, please observe the graph. As the pressure increases, PV value decreases first. That means at first these gases, the gases like carbon monoxide, methane, carbon dioxide, etc. shows negative deviation first. Then the pressure increases, the PV value also increases. That means the gases show positive deviation. The gases show positive deviation. Okay. Then very important points. A gas which obeys ideal gas equation under all conditions of temperature and pressure is called ideal gas. Real gases deviate from ideal behavior, hence the real gases are also known as non-ideal gas. Then real gases approach ideal behavior only at low pressure and high temperature. Then as the pressure increases and the temperature decreases, the deviation of gases from ideal behavior also increases. Okay? The extent of deviation of real gases from ideal behavior depends on nature of gas. The extent of deviation of real gases from ideal behavior is expressed in terms of compressibility factor set. Yes. The compressibility factor of a gas is equal to PV by nRT. Then, for ideal gas, the compressibility factor Z equal to 1. Yes, when Z equal to 1, PV equal to nRT into 1. PV equal to nRT, Z equal to 1, PV by nRT equal to 1 or PV equal to nRT. Okay, that means for ideal gas, Z equal to 1. That is PV by nRT equal to 1. Okay. Then, but for real gases, the value of compressibility factor Z is not equal to 1. Then, the extent of deviation of real gases can be studied by plotting a graph between compressibility factor and pressure. The compressibility factor values of different gases, yes, plotted here, plotted along the y-axis, and the corresponding pressures plotted along the x-axis. We know that for ideal gas, the value of Z is always 1. Okay? But for real gases show either positive deviation or negative deviation. Okay. If the value of Z is greater than 1, it is called positive deviation. It is called positive deviation, and the gas is less compressible than expected from ideal gas behavior. Okay. Yes. For example, the gases like hydrogen and helium, the value of Z is always greater than 1. When the pressure increases, the value of compressibility factor value of hydrogen and helium increases continuously. Okay, then for hydrogen and helium, Z is greater than 1. This means that these gases cannot be easily compressed and therefore cannot be easily liquefied. Okay. Then if the value of Z is less than 1, it is called negative deviation. It indicates that the gas is more compressible than expected from ideal gas behavior. Here, for nitrogen, methane, carbon dioxide, Z is less than 1. Here Z is less than 1. This means that these gases can be easily compressed and therefore it can be easily liquefied. Under ordinary pressure, that is 1 to 10 bar, the value of compressibility factor of all gases is almost close to 1. Okay, that means at very low pressure, the value of compressibility factor value of all real gases, okay, nearly equal to 1. This means that the deviations are so small and that the gases tend to behave nearly ideal. That means what? When pressure decreases, temperature increases, the extent of deviation from ideal behavior also increases. All the real gases show ideal behavior at low pressure and high temperature. Okay, at low pressure, at ordinary pressure. Okay, that means yes, 1 to 10 bar pressure, the compressibility factor value of all real gases nearly equal to 1. That means at low pressure and high temperature, all the real gases show ideal behavior. Okay, here you have to study one important term, Boyle's temperature or Boyle's point. What is meant by Boyle's temperature or Boyle's point? The Boyle's temperature of nitrogen gas is 323 Kelvin. Okay, and the Boyle's temperature of hydrogen gas is 108 Kelvin. Then what is meant by Boyle's temperature or Boyle's point? The temperature at which a real gas behaves like an ideal gas over appreciable range of pressure is called Boyle's temperature or Boyle's point. Okay, the temperature at which a real gas shows ideal behavior over an appreciable range of pressure is called Boyle's temperature or Boyle's point. Then, why do real gases deviate from ideal behavior? Okay, causes of deviation from ideal behavior. The causes of deviation of real gases from ideal behavior can be explained on the basis of two wrong postulates of kinetic molecular theory of gas. The first postulate is there is no force of attraction between gas molecules. The second postulate is the volume occupied by gas molecule is negligible as compared to total volume of gas. Okay. Yes. The first postulate is related with the molecular attraction. Okay, and the second postulate is related with the molecular volume. Yes. Okay, molecular attraction, and the second postulate is related with the molecular volume. Okay. The first postulate is true only at low pressure and high temperature. Okay. Yes, at low pressure and high temperature, the gas molecules are separated by very large distance. Then there is no force of attraction between gas molecule. Okay. But the molecules in gases have weak force of attraction amongst themselves. Otherwise, the gas never be liquefied. So, gas molecule തമ്മിൽ attractive force ഇല്ലെങ്കിൽ ഗ്യാസിനെ നമുക്ക് ഒരിക്കലും liquefy ചെയ്യാൻ പറ്റില്ല. Yes. But at high pressure and low temperature, yes, the gas molecules come closer. The gas molecules come closer. Okay, the gas molecules come closer, and some force of attraction operates between the gas molecules. When pressure increases, gas molecules അടുത്തേക്ക് വരുന്നു. അപ്പോൾ ഗ്യാസ് മോളിക്യൂൾ തമ്മിലുള്ള interparticle distance decrease ചെയ്യുന്നു. Then there is no doubt some force of attraction, yes, operates between the gas molecules. Then the second cause is related with the molar volume. Okay, thus okay. Then the second postulate is also true at low pressure and high temperature. At high pressure and low temperature, the total volume of the gas decreases considerably, while the volume of the gas molecule remains the same. Thus, under these conditions, means high pressure and low temperature, the volume of gas molecule is not negligible as compared to total volume of gas. Okay, ഇപ്പോൾ നമുക്കറിയാം ഗ്യാസിൻ്റെ വോളിയം എന്നത് അത് ഒക്യുപ്പൈ ചെയ്യുന്ന വെസലിൻ്റെ വോളിയമാണ് അല്ലേ. ദാറ്റ് ഈസ് ദ ടോട്ടൽ വോളിയം ഓഫ് ഗ്യാസ്. സപ്പോസ് ദ വോളിയം ഓഫ് ദിസ് വെസൽ ഈസ് 1 liter. The total volume of the gas becomes 1 liter. Okay, then the gas molecules are separated by larger distance. ഇവിടെ കൂടുതലും എന്താണുള്ളത്, empty space ആണുള്ളത്. അപ്പോൾ ഇവിടെ ഗ്യാസ് മോളിക്യൂളിൻ്റെ സൈസ് വളരെ ചെറിയ സൈസിലുള്ള ഗ്യാസ് മോളിക്യൂൾസിനെ ഒക്യുപ്പൈ ചെയ്യാൻ ആവശ്യമായിട്ടുള്ള വോളിയം, the volume of the gas, that is the actual volume of the gas, is very less as compared to the total volume, that is 1 liter. It may be 0.001 liter, the actual volume. But according to kinetic theory, the actual volume, the volume occupied by the gas molecule is negligible as compared to total volume. Yes, that means this postulate is true only at a low pressure and high temperature. Then, please listen. When pressure increases and temperature decreases, the gas molecules come closer, and here the total volume decreases considerably. The total volume decreases considerably. Okay, the total volume, yes, becomes 0.004 liter. The total volume may be 0.001 liter. But the total volume decreases considerably. But actual volume of the gas molecule remains same. Gas molecule ശരിക്കും ഒക്യുപ്പൈ ചെയ്യാൻ ആവശ്യമായിട്ട് വോളിയം എത്ര തന്നെയാണ്, 0.001 ലിറ്റർ ആണ്. അപ്പോൾ ഹൈ പ്രഷറിൽ ലോ ടെമ്പറേച്ചറിൽ ഈ ടോട്ടൽ വോളിയമായിട്ട് കമ്പയർ ചെയ്യുമ്പോൾ ഈ ആക്ച്വൽ വോളിയത്തെ നമുക്ക് ഒരിക്കലും നെഗ്ലക്റ്റ് ചെയ്യാൻ പറ്റില്ല. ഓക്കെ, നെഗ്ലക്റ്റ് ചെയ്യാൻ പറ്റില്ല. The actual volume is almost the volume occupied by the gas almost becomes equal to the total volume of gas. Okay, that means when pressure increases, temperature decreases, gas molecules come closer, and some force of attraction operates between the gas molecule, and total volume of the gas decreases considerably. Hence, the extent of deviation from ideal behavior also increases. That means when pressure increases, temperature decreases, the deviation from ideal behavior also increases. That means all the real gases show ideal behavior at low pressure and high temperature. In 1873, Van der Waals applied corrections for both defects, molecular, that is molecular volume and molecular attraction. He put forward a modified equation, the Van der Waals equation. Yes, Van der Waals equation. The equation for real gas is Van der Waals equation. Van der Waals equation is applicable for real gases. Please listen to the equation. For n moles of gas, the equation is P plus n squared A by B squared into V minus NB equal to nRT. Then for 1 mole of gas, the Van der Waals equation becomes what? P plus A by V squared into V minus B equal to RT. Okay, here A and B are called Van der Waals gas constants. The value of A and B depends on the nature of gas. The value of A and B depends on the nature of gas. Okay, the constant, the Van der Waals constant, A is a measure of intermolecular force of attraction. The value of A is a measure of intermolecular force of attraction. Okay, intermolecular force of attraction. The value of A is a measure of intermolecular force of attraction. Okay, greater the value of A, the Van der Waals constant A, greater is the strength of intermolecular force. Okay, then the gases having higher value of A can be easily liquefied. Okay, when the value of the Van der Waals constant A increases, the strength of intermolecular force increases, then yes, these gases are easily liquefied. Then next, the constant B is a measure of the effective size of molecules. The effective size of molecules. Size of molecules. Yes, the Van der Waals equation represents the equation for real gases. For n moles of gas, the equation is P plus n squared A by V squared into V minus NB equal to nRT, and here A and B are Van der Waals gas constants. Okay, and here the value of A and B depends on the nature of gas. A is a measure of the strength of intermolecular force of attraction, and B is the measure of the effective size of molecules. Then what are the main differences between ideal gas and real gas? Number one, we know ideal gas obeys all the gas laws at all temperature and pressure, but real gas obeys gas law only under low pressure and high temperature. And the second difference, ideal gas obeys ideal gas equation PV equal to nRT, but real gas obeys Van der Waals equation, that is P plus n squared A by V squared into V minus NP equal to nRT. Then, in the case of ideal gas, the volume occupied by gas molecule is negligible as compared to total volume of gas. ഇതാണ് കൈനറ്റിക് തിയറി പറയുന്ന ഒരു പോസ്റ്റുലേറ്റ്. ഇത് ഐഡിയൽ ഗ്യാസിന്റെ കേസിൽ ഓക്കെയാണ്. But in the case of real gas, we can say volume occupied by gas molecule is not negligible as compared to total volume of gas. And the last difference, the case of ideal gas, the force of attraction between gas molecule is negligible, or we can say there is no force of attraction between gas molecule if the gas is ideal. But in the case of the real gas, the force of attraction between gas molecule is not negligible. Okay, these are the main differences between ideal gas and real gas. Okay, students, in my next class, I will start new chapter in chemistry, thermodynamics. Okay, goodbye, study well.